August 29th, 1949, 7 a.m. local time. A barren stretch of steppe in northeastern Kazakhstan that officially didn't exist. Inside a concrete bunker buried 6 meters underground, Soviet scientists made final preparations. Through reinforced periscopes, they could see nothing but endless flat desert, exactly what Moscow wanted. No mountains to contain the blast, no valleys to channel radiation, just 18,000 square kilometers of absolutely nothing. Or so the maps claimed. But here's what makes this story extraordinary. The Soviet Union was about to detonate its first atomic bomb in a location that had no roads, no power, no water supply, and technically no name. American intelligence didn't even know Kazakhstan existed as a potential test site. They were watching Siberia. The site was so secret that it would take the West 4 years to locate it, and the engineering required to build it, it makes the Manhattan Project look straightforward by comparison. Because unlike the Americans at Alamogordo, who tested their device in accessible desert 200 miles from Los Alamos, Soviet engineers had to construct an entire nuclear testing facility 1,800 kilometers from the nearest major city, in a region where summer temperatures hit 45 degrees Celsius, winter plunged to minus 40 degrees Celsius, and the nearest railroad was 250 kilometers away across terrain that turned to impassable mud 6 months of the year. This is the story of how Soviet engineers solved the impossible problem of building Stalin's atomic testing ground from absolutely nothing, and why the solution they created would serve as the blueprint for nuclear testing sites worldwide. But before we understand how they built the polygon, we need to understand why Kazakhstan's wasteland was actually the only choice the Soviets had. In early 1947, Soviet Atomic Project Director Igor Kurchatov faced a problem that kept him awake at night. The RDS-1 bomb, their copy of the American Fat Man design, was nearly ready, but they had nowhere to test it. The selection criteria seemed designed to eliminate every location in the Soviet Union. First, isolation. The test site needed to be at least 200 kilometers from any significant population center. Stalin's paranoia demanded absolute secrecy, which meant no witnesses. But more importantly, Soviet radiation safety protocols, borrowed from captured German research, specified minimum evacuation distances that were actually more conservative than American standards. Second, geological stability. The site needed bedrock close to the surface to anchor the 37-meter tower that would hold the bomb. Soft soil wouldn't work. The tower had to remain perfectly vertical, despite the device weighing over 4,700 kilograms. Third, flat terrain extending at least 20 kilometers in all directions. Soviet physicists needed clear line of sight for instruments to measure blast effects, thermal radiation, and shockwave propagation. Unlike the Americans, who had the luxury of New Mexico's Jornada del Muerto basin naturally protected by mountains, the Soviets needed to find or create their own controlled environment. Fifth, minimal rainfall. Radiation dispersal calculations assumed dry conditions. A rain could create unpredictable contamination patterns. And finally, the requirement that seemed to contradict all others, the site needed an existing population nearby to study radiation effects on humans, animals, and structures. Kurchatov presented Stalin with 19 potential locations in May 1947. The General Secretary rejected 18 within minutes. Only one site remained, the Semipalatinsk region of northeastern Kazakhstan, a place so remote that even NKVD maps listed it as uninhabited steppe.
But those maps were catastrophically wrong, and that error would create an engineering challenge and a human tragedy that Soviet planners never anticipated.
When Soviet survey teams arrived in Kazakhstan in late 1947 to assess the site selected by Lavrentiy Beria, Stalin's ruthless security chief who headed the atomic project, they discovered something Soviet maps didn't show. The region wasn't empty. Kazakh nomads moved seasonally across the steppe with sheep, horses, and cattle. Villages dotted the landscape along the Irtysh River. The nearest substantial town, Semipalatinsk, had over 100,000 residents, just 150 kilometers from the proposed ground zero. According to later health surveys, approximately 1.5 million people lived within 300 kilometers of the test zone. This wasn't the uninhabited wasteland Beria had claimed. This created an immediate ethical and logistical nightmare. American planners at Alamogordo had evacuated exactly one ranching family, the MacDonald family, who owned the only property within the Trinity test zone. The Soviets faced potential displacement of over 1 million people. Stalin's solution was characteristically brutal and practical. Don't evacuate, don't inform, simply prohibit access to a core exclusion zone and classify everything. But this decision created an unprecedented engineering challenge. Unlike Alamogordo, where the nearest human beings were 30 kilometers in a single direction, Soviet engineers now had to design a test site that would function with populated areas at varying distances in all directions. They needed infrastructure to monitor radiation spread across hundreds of kilometers, medical facilities to track health effects, officially for scientific purposes, though the real reason was never stated to the Kazakh population. And most critically, they needed construction methods that could work with limited labor, because bringing in tens of thousands of workers would reveal the site's existence. The solution would require engineering innovation on a scale the Americans never attempted. And it all started with a railroad that shouldn't have been possible to build.
Every nuclear test site begins with a transportation problem. Los Alamos had existing roads from Santa Fe. Hanford had the Columbia River and nearby rail connections. The Nevada test site would later benefit from Las Vegas's infrastructure. The Semipalatinsk polygon had nothing. The nearest railroad, the Turkestan-Siberia line, stopped at a station 250 kilometers southwest of the chosen ground zero. Between the existing rail network and the test site lay the Kazakh steppe, flat, treeless, and deceptively hostile terrain. In spring, snowmelt turned the clay soil into bottomless mud that swallowed trucks whole. In summer, the same soil baked concrete hard and cracked into fissures a meter deep. In winter, blizzards created snowdrifts that buried entire convoys. Soviet construction planners calculated that conventional road building would take 3 years. Kurchatov had given them 18 months. Their solution was brilliantly unconventional. Don't fight the terrain, float above it. Soviet engineers implemented a military technique developed during the war, laying prefabricated steel mesh directly on the steppe surface, anchored with driven piles reaching down to hardpan clay beneath the topsoil. The mesh, originally designed for temporary airfield construction, distributed vehicle weight across a wide surface area, preventing sinking during the mud season. In winter, snow would blow through the mesh rather than accumulating in drifts. But the real challenge was the railroad extension itself. Between mid-1947 and early 1948, labor battalions from the Gulag system constructed a spur line from the existing railway to a new station designated only as Point 10. They worked in shifts around the clock, laying track directly on the steppe using methods that violated every principle of railroad engineering. Standard Soviet practice required 60 centimeters of crushed stone ballast beneath the ties. This track had minimal ballast, just rails spiked to wooden ties placed on leveled earth. It was temporary construction designed to last exactly as long as needed,
through the test preparation period before being upgraded or relocated. But it worked. The first locomotive reached Point 10 in December 1947, carrying construction equipment and the first wave of technical personnel. The track would eventually be upgraded and would remain in service for over 4 decades. With transportation solved, engineers faced their next impossible challenge: building a bomb tower with limited materials, no heavy equipment, and no construction blueprints from which to work.
In early 1948, Soviet structural engineers received specifications that seemed designed to be impossible. The RDS-1 bomb, weighing 4,700 kilograms, needed to be detonated exactly 37.5 meters above the ground. This height, calculated by physicist Yakov Zeldovich, would maximize the blast wave's destructive radius while allowing instruments to measure all 3 phases of nuclear detonation. But the tower supporting this weight needed to meet contradictory requirements: strong enough to hold nearly 5 tons in winds up to 30 meters per second, common in the Kazakh steppe; light enough to be constructed without heavy crane equipment, which couldn't reach the site; tall and stable despite having limited foundation depth. Bedrock lay 8 meters down, and they lacked equipment to drill that deep in the available time. And perhaps most challenging, the tower had to be precise. If the bomb sat even 2 meters off the designated height, months of calibration for the measurement instruments would be worthless. Soviet engineers studied whatever intelligence they had on the Alamogordo tower design, 100 feet of steel construction assembled by experienced American steelworkers using mobile cranes. They had none of those resources. Instead, they turned to Soviet industrial salvage and improvisation. The design that emerged used decommissioned components from various sources, transported thousands of kilometers by rail. 4 main legs constructed from large-diameter steel pipe formed a square base approximately 20 meters per side. Cross-bracing used salvaged pipeline sections welded together on site. The foundation solution avoided the need for deep drilling. Instead of deep piles, they poured massive concrete pads directly on the surface. The sheer weight of these pads, dozens of tons each, provided stability through mass alone, a technique borrowed from temporary military bridge construction. Assembly used a method adapted from temporary industrial structures. The tower was built in sections, then raised using manual winch systems and temporary guy wires. Teams working in rotation took nearly a week to raise the structure to vertical. But the most critical component was the platform that would hold the bomb itself. This platform, several meters square, needed to be absolutely level and vibration-free. Soviet physicists feared that even slight movement during the countdown could affect the symmetrical implosion required to detonate plutonium. Engineers used vibration-dampening techniques adapted from other Soviet industries, mounting the bomb cradle on shock absorbers to prevent any movement that might compromise the device. By May 1949, the tower stood complete. Surveying confirmed it was vertical within acceptable tolerance, and the platform remained level across its entire surface. But the tower was just one piece of infrastructure. The real engineering marvel was the measurement system that would capture data from a nuclear explosion, using technology the Americans had spent years developing, which the Soviets had to replicate in less than 2 years.
The RDS-1 test would last exactly 0.003 seconds from initial detonation to full fireball expansion. In that 3-millisecond window, Soviet physicists needed to capture data that would validate every calculation they'd made.
The challenge: how do you measure something that creates temperatures of 100 million degrees, pressure waves traveling at 500 meters per second, and electromagnetic pulses that destroy electronic equipment, using 1940s analog technology? Chief physicist Yuli Khariton designed a measurement network of unprecedented complexity. At distances of 500, 1,000, 2,000, 5,000, and 10,000 meters from ground zero, engineers constructed dozens of instrument bunkers. Each bunker followed an identical design: a reinforced concrete structure with thick walls, buried underground with only instrument ports and periscopes extending to the surface. The concrete came from a mobile batching plant, among the first of its kind in Soviet engineering, capable of producing concrete on-site despite having no local water source. Engineers solved this by drilling wells to the water table dozens of meters down, using adapted oil field drilling equipment. Inside each bunker, instruments recorded specific phenomena. Blast pressure gauges measured shock wave overpressure using mechanical drum recorders, simple devices where needles scratched measurements onto rotating wax cylinders. No electronics to be destroyed, purely mechanical reliability. Thermal radiometers measured heat using thermopile sensors connected to mirror galvanometers. The mirrors reflected light beams onto photographic paper, creating a permanent record of thermal pulse intensity. Seismographs recorded ground shock transmission through the steppe geology, data that would later help distinguish nuclear tests from earthquakes, critical for monitoring future American tests. High-speed cameras developed at Soviet optical institutes captured the fireball's evolution at high frame rates. These cameras used mechanical shutters synchronized by clockwork mechanisms because electronic timing would be destroyed by the electromagnetic pulse. But the most audacious instrumentation was the effects target array. At measured distances, engineers constructed a test city, dozens of buildings representing different types of Soviet architecture: wooden residential buildings, brick apartment blocks, concrete bunkers. Each structure contained pressure sensors and dosimeters to measure radiation exposure. Unlike the Americans, who used primarily military structures at Trinity, Soviet engineers built civilian targets. The reason was grimly practical. Stalin wanted data on how Soviet cities would withstand an American attack. The most controversial elements were the animal test subjects, over 1,500 pigs, goats, and sheep, selected because their physiology approximates human radiation response. They were placed at various distances in protective structures of different types. The entire instrumentation system connected to a central command bunker approximately 10 kilometers from ground zero. This bunker, designated as the main observation point, is where Kurchatov and senior scientists would observe the test. By August 1949, everything was ready, but the final challenge would prove the most nerve-wracking: actually getting the bomb to the tower.
August 20th, 1949, the RDS-1 device arrived at Point 10 station in a specially modified rail car. The bomb, codenamed Izdelye 501, Product 501, had been assembled at Arzamas-16, the secret nuclear weapons laboratory. The journey across the Soviet Union took several days, moving primarily at night through remote areas, with NKVD security battalions guarding every kilometer. Now came the terrifying part: transporting a fully assembled atomic bomb across rough terrain to the tower, then raising it 37 meters into the air. American engineers at Alamogordo had assembled their device at the base of the tower, then used a hydraulic system to slowly raise it. The Soviets had no such specialized equipment. Instead, they used a modified heavy truck fitted with a lifting platform. The bomb sat in a special cradle lined with padding, secured carefully to prevent any jarring during transport.
The convoy moved at walking speed, literally. Personnel walked ahead of the vehicle, filling holes and clearing obstacles. The journey to the tower site took many hours. At the tower, engineers faced their most anxious operation. The bomb had to be raised to the platform using a hand-operated winch system, moving slowly to prevent any jarring that might damage the sensitive implosion lens system. The process took most of a day, hours during which engineers manually operated lifting equipment, while Kurchatov and senior physicists watched from a safe distance, knowing that any mistake could either destroy the device or potentially cause an accident. In the early morning hours of August 29th, the bomb was in position. Lead physicist Yakov Zeldovich climbed the tower to make the final electrical connections, working carefully to connect the firing circuits to the buried cables that would carry the detonation signal. At 6 a.m., all personnel evacuated to the observation bunkers. At 7 a.m., Kurchatov gave the order. An electrical signal traveled through buried cables to the tower. The RDS-1 exploded with a yield of 22 kilotons, matching calculations exactly. The shock wave reached the control bunker 30 seconds later. Through periscopes, engineers watched the mushroom cloud rise to 12 kilometers. The Semipalatinsk polygon had succeeded. Stalin's desert atom had proven Soviet engineering could match American nuclear capabilities. But the story of the polygon was just beginning. What happened next would make it the most used nuclear test site in history.
Between 1949 and 1989, the Semipalatinsk polygon would host 456 nuclear tests, more than any other site on Earth except the Nevada test site. The infrastructure that Soviet engineers built from nothing became a permanent installation. The temporary railroad became permanent. The improvised roads were replaced with paved highways. The mobile concrete plant became a full industrial complex. Point 10 Station grew into Kurchatov, a closed city that wouldn't appear on public maps until 1991. It had schools, hospitals, and research institutes, all built around the infrastructure created for that first test. The engineering techniques pioneered at Semipalatinsk spread worldwide. When China established the Lop Nur test site in 1964, they consulted with Soviet engineers who had worked at the polygon. When France built its Sahara test sites, they studied Soviet construction methods. When the United States expanded the Nevada test site, they adopted several Soviet instrumentation techniques. But the human cost was catastrophic. The 1.5 million people within the affected zone were never evacuated, never warned. Soviet medical researchers documented radiation effects on the population as part of scientific data collection, effects that included elevated cancer rates, birth defects, and shortened lifespans that persist to this day. In 1989, Kazakh activist Olzhas Suleimanov founded the Nevada Semipalatinsk movement, uniting victims of nuclear testing worldwide. The movement's protests eventually forced Moscow to close the site. The last test occurred on October 19, 1989. On August 29, 1991, exactly 42 years after the first test, newly independent Kazakhstan officially closed the polygon forever. Today, the site remains largely restricted. The concrete bunkers still stand, their periscopes still pointing toward ground zero. The tower from the first test was vaporized. Nothing remains but a monument marking where Stalin's desert atom forever changed the nuclear age. The engineering achievement remains undeniable. Soviet engineers built a fully functional nuclear test site in conditions that seemed designed to make it impossible. They did it faster, with fewer resources, and in harsher conditions than many other nuclear programs in history. The radiation monitors they installed to measure that first test?
Many still function, now measuring the long-term contamination that will persist for thousands of years.
The Semipalatinsk polygon represents one of history's most extreme examples of engineering under impossible constraints. Soviet engineers built a complete nuclear testing infrastructure in approximately 18 months in a location with no water, no power, no roads, and no construction materials, all while maintaining absolute secrecy. Today, satellite imagery has revealed details that were state secrets for decades. The scale of the construction is staggering: over 1,000 buildings, hundreds of kilometers of roads, multiple airfields, and that original railroad, all built from scratch in Kazakhstan's wasteland. The techniques developed there influenced every nuclear testing program that followed. Underground testing methods used worldwide originated from experiments at Semipalatinsk. Radiation monitoring networks, now standard at all test sites, trace their design to Soviet innovations. Even modern seismic verification used in nuclear treaties relies on instrumentation concepts first proven in those concrete bunkers on the Kazakh steppe. The site itself is now being remediated, a cleanup project expected to continue for years at enormous cost. Engineers are discovering that Soviet construction was so robust that some bunkers remain perfectly intact over 70 years later, their instruments still in place, still measuring radiation from tests that occurred before most of us were born. It's a reminder that engineering excellence exists separately from the purposes it serves. The engineers who built Stalin's desert atom created solutions to problems that seemed impossible, even as those solutions enabled one of history's most controversial military programs.
If this story of Soviet nuclear engineering impressed you, you'll want to see how the Americans faced different but equally challenging problems building Oak Ridge, the uranium enrichment facility that required more electricity than most countries used, constructed in Tennessee in absolute secrecy with 75,000 workers who didn't know what they were building. Make sure you're subscribed and notifications are on, because next week we're covering the French nuclear program, how France built its own atomic testing site in the Sahara Desert under even harsher conditions, with less international help and while fighting a war in Algeria at the same time. What engineering problem in military history amazes you most? Drop a comment below. I read every single one, and your suggestions often become future videos. Thanks for watching. Remember, history isn't just about what happened, it's about how brilliant minds solved problems no one had solved before.